The universe we see, stars, galaxies, even our own planet is just the tip of a cosmic iceberg. In fact, everything we can observe, touch, or measure makes up less than 5% of what's actually out there. The rest, a vast, invisible realm dominated by two mysterious forces, dark matter and dark energy. Together, they make up 95% of the universe, yet we can't see them, touch them, or even fully understand them. So what are they, and more importantly, which one is truly in control of the cosmos? Dark matter, with its gravitational pull that holds galaxies together, or dark energy, the enigmatic force driving the universe to expand faster and faster. These invisible giants shape the fate of everything we know, and today we're diving deep into their secrets. From their origins to their ultimate influence, we'll uncover the invisible forces that rule the universe and why understanding them could change everything we think we know about reality itself. Look up at the night sky and you'll see a breathtaking tapestry of stars, planets, and galaxies. These luminous objects are what we call the observable universe, the part of the cosmos we can see, measure, and study. But here's the mind-blowing part. Everything we can observe with telescopes, from the tiniest speck of starlight to the most massive galaxy clusters, accounts for just 5% of the universe. That's right, only 5%. The rest of the cosmos, a staggering 95%, is made up of something we can't see, touch, or even fully comprehend. This invisible majority is dominated by two mysterious entities, dark matter and dark energy. So, how did we even begin to uncover the existence of these invisible forces? It all started with a cosmic puzzle. In the 1930s, astronomer Fritz Zwicky noticed something strange while studying galaxy clusters. The galaxies were moving so fast that, based on the visible matter alone, they should have flown apart. But they didn't. Something unseen was holding them together, something with enough gravitational pull to keep entire galaxies in place. Zwicky called this unseen force dark matter. Decades later, in the late 1990s, scientists made another groundbreaking discovery. They found that the universe wasn't just expanding, it was expanding faster and faster over time. This acceleration defied all expectations, pointing to an unknown energy pushing the cosmos apart. This mysterious force became known as dark energy. These discoveries didn't just rewrite the textbooks, they completely reshaped our understanding of the universe. Dark matter, with its gravitational influence, acts like cosmic glue, holding galaxies and galaxy clusters together. Dark energy, on the other hand, is like an invisible hand, stretching the fabric of space itself and driving the universe's accelerated expansion. Together, they form the backbone of the cosmos, even though we can't directly observe them. But how did we go from spotting anomalies to realizing these invisible forces were everywhere? The clues were hidden in the way galaxies spin, the way light bends around massive objects, and even in the faint echoes of the Big Bang. Each of these observations painted a clearer picture of a universe dominated by forces we can't see but can't ignore. And that leads us to the next big question: how do we study something we can't even detect directly? In the 1930s, the cosmos presented astronomers with a puzzle they couldn't ignore. Fritz Zwicky, a Swiss astronomer studying the Coma cluster of galaxies, noticed something odd. The galaxies within the cluster were moving at speeds that defied logic. Based on the amount of visible matter, stars, gas, and dust, the galaxies should have been flying apart. But they weren't. Something invisible, something far more massive than anything we could see, was holding them together. Zwicky called this mysterious substance dark matter, a term that would go on to define one of the greatest mysteries in modern science. But Zwicky's discovery was just the beginning. Decades later, in the 1970s, astronomer Vera Rubin took the investigation further. By studying the rotation curves of galaxies, how stars orbit around galactic centers, she found something startling. Stars on the outer edges of galaxies were moving just as fast as those near the center, a behavior that shouldn't be possible if only visible matter were present. Rubin's work confirmed Zwicky's suspicions. Dark matter wasn't just a quirk of galaxy clusters. It was everywhere, woven into the very fabric of the cosmos, influencing the motion of stars and galaxies on a massive scale. Yet, even with this growing body of evidence, dark matter remained elusive. We couldn't see it, but we could see its effects. One of the most compelling clues came from a phenomenon called gravitational lensing. When light from a distant object, like a galaxy or quasar, passes near a massive object, the gravity of that object bends the light, acting like a cosmic magnifying glass. But here's the twist: sometimes the bending is far greater than what the visible matter alone could cause. This extra bending is the fingerprint of dark matter, warping space and light in ways that reveal its presence. Despite all these clues, one question remains unanswered. What is dark matter made of? Is it a new kind of particle, something entirely different from the atoms and molecules we know? Or is it something even stranger? Scientists have proposed countless theories, from weakly interacting massive particles WIMP to actions and beyond. Yet, after decades of searching, we still haven't detected dark matter directly. It's a cosmic ghost, leaving traces of its existence everywhere but slipping through our grasp every time we try to pin it down. This ongoing mystery sets the stage for its cosmic counterpart, dark energy. While dark matter pulls the universe together with its gravitational grip, dark energy does the opposite. It pushes the cosmos apart, accelerating its expansion. Together, these two invisible forces shape the fate of the universe, one pulling, the other pushing, in a cosmic tug of war that's been raging since the dawn of time. But how did we discover dark energy, and how does it fit into this grand cosmic puzzle? That's where our journey takes us next. In the late 1990s, the universe threw scientists another curveball, one that would fundamentally change our understanding of cosmic evolution. Two independent teams of astronomers studying distant supernova made a startling discovery. The universe wasn't just expanding, as Edwin Hubble had shown decades earlier. It was expanding faster and faster over time. This unexpected acceleration defied everything we thought we knew about gravity and the fate of the cosmos. The discovery was so groundbreaking that it earned the teams the Nobel Prize in Physics in 2011. So, what was causing this bizarre behavior? Enter dark energy, a mysterious force that acts as a counterweight to gravity. While dark matter pulls galaxies together, dark energy does the opposite, pushing them apart with a kind of cosmic repulsion. Think of it like this: if the universe is a balloon, dark energy isn't just inflating it, it's blowing air into the balloon faster and faster, making it stretch at an ever-increasing rate. The key to this discovery lay in a specific type of supernova known as Type Ia. These stellar explosions shine with a consistent brightness, making them ideal standard candles for measuring cosmic distances. By comparing the brightness of these supernovae at different distances, astronomers could track how the universe's expansion rate has changed over time. What they found was astonishing. The farther away the supernova were, the faster their galaxies appeared to be moving away from us. This wasn't just a gentle expansion, it was a runaway acceleration driven by something invisible and powerful. Dark energy was proposed as the explanation, a force that permeates the fabric of space itself. But here's the twist: unlike gravity, which weakens with distance, dark energy's repulsive effect actually grows as the universe expands. This means that over time, dark energy's influence becomes even stronger, pushing galaxies apart at an ever-increasing pace. It's like an unstoppable cosmic engine, driving the universe toward a future where galaxies may eventually drift so far apart that they become invisible to one another. This revelation was a game changer. For decades, scientists had assumed that gravity would eventually slow down the universe's expansion. potentially leading to a big crunch where everything collapses back in on itself. But dark energy flipped the script entirely. Instead of a cosmic collapse, the universe seems destined to expand forever, growing colder and more diffuse as galaxies are pulled apart by this invisible force. Yet, for all we've learned, dark energy remains one of the greatest mysteries in science. What is it exactly? Is it a property of space itself, as Albert Einstein once speculated with his concept of the cosmological constant? Or is it something entirely new, a force we've yet to fully understand? These questions are at the heart of modern cosmology, driving scientists to explore the universe's deepest secrets. And while dark energy pushes the cosmos apart, its counterpart, dark matter, continues to hold it together. This cosmic tug of war between the pull of dark matter and the push of dark energy shapes the fate of the universe. But how do these two forces interact on the grandest scales? And what does their balance mean for the future of everything we know? That's where our journey takes us next. So, what exactly sets dark matter and dark energy apart? And how do they shape the universe in such opposing ways? Let's break it down. Dark matter, as we've seen, is the cosmic glue, the unseen scaffolding that holds galaxies and galaxy clusters together. Without it, stars on the outer edges of galaxies would fly off into the void, unbound by gravity. Think of it like the invisible threads of a spider web, keeping everything connected even though you can't see the strands themselves. Its gravitational pull is so strong that it bends light, warps spacetime, and dictates the motion of entire galaxies. Yet, despite its immense influence, dark matter remains invisible, detectable only through its effects on the visible universe. Dark energy, on the other hand, is the cosmic rebel, the force that refuses to play by gravity's rules. Instead of pulling things together, it pushes them apart, driving the universe's expansion faster and faster. Picture dark energy as the wind inflating a balloon, stretching the fabric of space itself. While dark matter works to keep galaxies intact, dark energy works against it, creating a cosmic tug of war that shapes the fate of the universe. What's fascinating is that both dark matter and dark energy share one key trait: invisibility. We can't see them, touch them, or even detect them directly. Yet their presence is undeniable, woven into the very fabric of reality. Dark matter reveals itself through its gravitational effects, while dark energy betrays its existence through the accelerating expansion of the universe. These two forces are like cosmic ghosts shaping everything we see and don't see without ever showing their faces. But how do scientists study these invisible entities? The answer lies in their subtle fingerprints on the cosmos. For dark matter, astronomers use tools like gravitational lensing, observing how light bends around massive objects to map its presence. They also study the rotation curves of galaxies, tracking how stars move to infer the distribution of unseen mass. Dark energy, meanwhile, is detected through the behavior of distant supernova, the cosmic microwave background, and the large-scale structure of the universe. By piecing together these clues, researchers can begin to unravel the mysteries of these invisible forces. The interplay between dark matter and dark energy is a delicate dance, one that determines the ultimate fate of the universe. Dark matter's gravity pulls galaxies together, creating the cosmic structures we see today, while dark energy's relentless push threatens to tear them apart. It's a battle of forces, each with its own role in shaping the cosmos. But what does this mean for the future of the universe? Will dark energy's expansion eventually overcome dark matter's grip, scattering galaxies into oblivion? Or is there a balance yet to be discovered? As we continue to explore these questions, one thing is clear: dark matter and dark energy are not just scientific curiosities, they are the architects of the universe, the invisible hands guiding its evolution. And while we may not yet fully understand them, each discovery brings us closer to unraveling the secrets of the cosmos. So, what's next in this cosmic journey? Let's dive deeper into how these forces shape the universe on the largest scales, and what their ultimate influence might mean for everything we know. Studying something we can't see might sound like a paradox, but when it comes to dark matter, scientists have become cosmic detectives, piecing together clues from the universe itself. One of the most powerful tools in this investigation is gravitational lensing. Imagine a massive object like a galaxy cluster sitting between us and a distant light source. The gravity of that cluster bends the light from the source, acting like a magnifying glass. But here's the catch: the amount of bending often exceeds what the visible matter alone could cause. This extra distortion, that's dark matter at work, warping space and revealing its presence through its gravitational fingerprint. Another key clue comes from the way galaxies rotate. In the 1970s, astronomer Vera Rubin discovered that stars on the outer edges of galaxies move just as fast as those near the center. This shouldn't happen if only visible matter were present. Gravity from stars and gas wouldn't be strong enough to keep those outer stars in orbit. The solution: a massive, invisible halo of dark matter enveloping the galaxy, providing the extra gravitational pull needed to explain these observations. It's like an unseen hand steadying the cosmic dance of stars. But dark matter's influence doesn't stop there. It also leaves its mark on the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light reveal how matter was distributed in the early universe. By studying these patterns, scientists can map the distribution of dark matter, showing how it shaped the cosmos over billions of years. It's like uncovering the blueprints of the universe with dark matter as the unseen architect. On Earth, the search for dark matter takes a different approach. Experiments like those at the Large Hadron Collider aim to recreate the conditions of the early universe, smashing particles together in hopes of producing dark matter particles. Meanwhile, deep underground, detectors like those in the LUX Zeppelin experiment wait patiently for a rare interaction between dark matter and ordinary matter. These efforts are like setting cosmic traps, hoping to catch a glimpse of something that's remained hidden for eons. Yet, despite all these tools, the nature of dark matter remains elusive. Is it made of weakly interacting massive particles, or WIMP hypothetical particles that barely interact with ordinary matter? Or could it be something entirely different, like actions ultra-light particles theorized to exist? The debate is far from settled, and each new experiment brings us closer to answers, or raises even more questions. As we continue to probe the mysteries of dark matter, one thing is certain: the tools we use to study it are as fascinating as the mystery itself. From bending light to smashing particles, each method offers a unique window into the invisible forces shaping our universe. But dark matter isn't the only invisible giant out there. Its counterpart, dark energy, presents its own set of challenges and opportunities for discovery. So, how do we study a force that's stretching the very fabric of space itself? That's where our journey takes us next. The quest to understand dark energy has led scientists to develop some of the most advanced tools in the history of astronomy. At the forefront of this effort is the Hubble Space Telescope, a marvel of engineering that has peered deeper into the cosmos than any telescope before it. By observing distant supernova, Hubble has provided critical data on how the universe's expansion has changed over billions of years. These observations are made possible by a special kind of stellar explosion known as Type Ia supernova, often called standard candles. Because these supernovas shine with a consistent brightness, they act like cosmic mile markers, allowing astronomers to measure vast distances across the universe with remarkable precision. It's like having a ruler that stretches across billions of light years, helping us map the accelerating expansion driven by dark energy. But Type Ia supernova aren't the only tool in the cosmic toolkit. Another key method involves studying baryon acoustic oscillations, or BAO. Imagine the early universe as a dense, hot soup of particles. Tiny ripples in this primordial soup created pressure waves, leaving behind a faint imprint in the distribution of galaxies we see today. These ripples act as a cosmic yardstick, helping scientists measure the universe's expansion over time. By mapping the distribution of galaxies and comparing it to these ancient ripples, researchers can track how dark energy has influenced the growth of cosmic structures. Then there's the cosmic microwave background, or CMB, the oldest light in the universe. This faint glow, dating back to just 380,000 years after the Big Bang, holds a treasure trove of information about the early cosmos. Tiny fluctuations in the CMB reveal how matter was distributed at the dawn of time, offering clues about the role of dark energy in shaping the universe's evolution. Together, these tools, supernova, BAO, and the CMB, paint a comprehensive picture of how dark energy has driven the universe's expansion from its earliest moments to the present day. Looking to the future, the Nancy Grace Roman Space Telescope promises to take this exploration to new heights. Set to launch in the mid-2020s, this next-generation observatory will map the cosmos with unprecedented precision, capturing the light of billions of galaxies and uncovering the subtle effects of dark energy on the universe's structure. With its wide field of view and advanced instruments, the Roman telescope will provide a deeper understanding of how dark energy has shaped the cosmos over billions of years. It's like opening a new chapter in the story of the universe, one where the mysteries of dark energy may finally come into focus. Yet, for all the progress we've made, the true nature of dark energy remains shrouded in mystery. Is it a property of space itself, as Einstein's cosmological constant suggests, or is it something entirely new, a force we've yet to fully comprehend? Some theories propose that dark energy could be a dynamic field, changing over time and interacting with other cosmic forces in ways we don't yet understand. Others suggest it might be connected to the very fabric of space-time, a fundamental aspect of the universe that we've only begun to explore. As we piece together these clues, one thing is certain: the study of dark energy is not just about understanding the universe's past, it's about uncovering its future. Will dark energy continue to accelerate the expansion, pushing galaxies farther apart until they vanish from view? Or could its influence change over time, altering the fate of the cosmos in ways we can't yet predict? These are the questions that drive scientists to push the boundaries of exploration, using every tool at their disposal to unravel the secrets of this enigmatic force. And as we continue this cosmic journey, the interplay between dark matter and dark energy becomes even more intriguing. How do these two invisible forces shape the universe on the largest scales? And what does their balance or imbalance mean for the ultimate fate of everything we know? The answers to these questions may lie just beyond the horizon, waiting to be discovered by the next generation of telescopes, experiments, and bold ideas. So, what exactly is dark energy? Is it a fixed property of space, a dynamic force, or something completely beyond our current understanding? To tackle this question, scientists have proposed several leading theories, each offering a unique perspective on this enigmatic force. One of the earliest and most enduring ideas comes from none other than Albert Einstein himself. In the early 20th century, Einstein introduced the concept of the cosmological constant, a term he added to his equations of general relativity to describe a uniform energy density inherent to space itself. At the time, he used it to explain a static universe, but when Edwin Hubble discovered the universe was expanding, Einstein famously called the cosmological constant his greatest blunder. Ironically, decades later, the discovery of dark energy revived this idea, suggesting that the cosmological constant might indeed describe the energy of empty space, driving the universe's accelerated expansion. But not everyone is convinced that dark energy is a constant. Another compelling theory proposes that dark energy could be a dynamic field, changing over time in both strength and behavior. This idea, known as quintessence, paints dark energy as something more fluid, like a cosmic wind that ebbs and flows. Unlike the cosmological constant, quintessence could interact with other forces or fields, potentially explaining why the universe's expansion rate appears to have changed over billions of years. It's a fascinating possibility, one that suggests dark energy might be more complex than we've imagined. Then there's the idea that dark energy might not be a separate force at all, but rather a sign that our understanding of gravity itself is incomplete. This is the heart of modified gravity theories, which propose that Einstein's theory of general relativity, while incredibly successful, might need tweaking on the largest scales. These theories suggest that what we perceive as dark energy could actually be the result of gravity behaving differently over vast cosmic distances. But while modified gravity offers an intriguing alternative, it faces significant challenges. So far, it hasn't been able to fully explain all the observations tied to dark energy, leaving many scientists skeptical. Of course, these aren't the only ideas on the table. Some researchers have speculated that dark energy could be linked to extra dimensions or even the mysterious nature of quantum vacuum energy. Others propose it might be a sign of new physics entirely, a fundamental force we've yet to discover. The possibilities are as vast as the cosmos itself, and each theory brings us closer to understanding the true nature of this invisible force. Yet for all the progress we've made, dark energy remains a puzzle. It's a reminder that the universe is far stranger and more complex than we often assume. And while we grapple with these questions, we can't forget its cosmic counterpart, dark matter. Just as dark energy pushes the universe apart, dark matter pulls it together, creating a delicate balance that shapes everything we see. But what connects these two invisible giants? Are they two sides of the same cosmic coin or entirely separate phenomena? As we continue to explore these mysteries, one thing is clear: the story of dark energy and dark matter is far from over. Each discovery, each new theory, brings us closer to unraveling the secrets of the universe and perhaps to understanding the ultimate fate of everything we know. Dark matter is a ghost in the cosmic machine, invisible yet undeniably present. But if we can't see it, what exactly is it made of? Scientists have proposed several leading candidates, each with its own unique properties and challenges. One of the most popular theories involves weakly interacting massive particles, or WIMP. These hypothetical particles are thought to be heavy, much heavier than protons, yet interact so weakly with ordinary matter that they pass through us like shadows. If WIMP exist, they could be everywhere, filling the universe in vast numbers, yet remaining virtually undetectable. Another intriguing possibility is the action, a particle so light it's almost weightless. Unlike WIMP, actions wouldn't rely on mass to make up dark matter. Instead, they'd exist in enormous quantities, like a cosmic sea of tiny, invisible particles. Actions are theorized to interact so feebly with ordinary matter that they'd be incredibly difficult to spot, but their sheer numbers could account for dark matter's gravitational effects. Then there's the idea of sterile neutrinos. Neutrinos are already known to science. They're nearly massless particles that stream through the universe, barely interacting with anything. But sterile neutrinos would be a heavier, even more elusive cousin, interacting only through gravity. If they exist, they could be the missing piece of the dark matter puzzle, blending seamlessly into the cosmic background. But how do we even come up with these ideas? Enter supersymmetry, a theoretical framework that predicts a whole family of new particles. According to supersymmetry, every particle we know, like electrons and quarks, has a heavier, invisible superpartner. One of these superparticles, such as the neutralino, could be the dark matter particle we've been searching for. Supersymmetry offers an elegant solution, but so far it remains unproven. Despite these compelling theories, direct evidence for dark matter particles has remained frustratingly out of reach. Experiments like Xenon and LUX are designed to detect the faintest hints of dark matter interactions. These detectors, often buried deep underground to shield them from cosmic radiation, wait patiently for a rare collision between a dark matter particle and ordinary matter. So far, they've turned up empty, but the search continues, driven by the hope of a breakthrough discovery. What makes dark matter so hard to detect? It all comes down to its nature. Dark matter doesn't emit, absorb, or reflect light. It's completely invisible. It also interacts so weakly with ordinary matter that it can pass through entire planets without leaving a trace. This makes it a ghostly presence felt only through its gravitational effects. Yet, despite its elusiveness, dark matter's influence is undeniable. It shapes galaxies, bends light, and even determines the large-scale structure of the universe. And that's the key point. Dark matter isn't just a curiosity, it's a cosmic architect. Without it, galaxies wouldn't hold together, and the universe as we know it wouldn't exist. Its gravitational pull creates the scaffolding for galaxies and galaxy clusters, dictating how they form and evolve. Dark matter is the unseen hand that guides the cosmos, shaping everything from the tiniest dwarf galaxy to the vast web of cosmic filaments that stretch across the universe. But as we continue to search for dark matter particles, another question looms. How does dark matter interact with its cosmic counterpart, dark energy? These two invisible forces, one pulling, the other pushing, shape the fate of the universe in ways we're only beginning to understand. And as we explore their interplay, we uncover even more questions about the nature of reality itself. So, what's next in the quest to unravel the mysteries of dark matter? From underground detectors to space-based observatories, scientists are using every tool at their disposal to chase this cosmic ghost. Each experiment brings us closer to answers or reveals new layers of the mystery. But one thing is certain, the story of dark matter is far from over, and its secrets may hold the key to understanding the universe itself. To truly grasp the universe's grand design, we need to understand how dark matter laid the foundation for everything we see today. Picture the early universe as a vast, chaotic sea of particles, with dark matter acting like an invisible scaffolding. Its gravitational pull, stronger than that of ordinary matter, began to draw particles together, creating dense regions known as dark matter halos. These halos became the cosmic seeds, the starting points for the formation of galaxies and galaxy clusters. Without dark matter's gravitational influence, the universe might have remained a featureless expanse, devoid of the intricate structures we observe today. But how exactly did this process unfold? To answer that, scientists turn to cosmological simulations, computer models that recreate the universe's evolution over billions of years. These simulations reveal a stunning web-like structure known as the cosmic web, where dark matter forms massive filaments connecting galaxies and galaxy clusters. These filaments are like the backbone of the universe, with dark matter acting as the glue that holds everything together. Ordinary matter, the stuff we can see, followed this dark matter blueprint, collapsing into these dense regions to form stars, planets, and eventually the galaxies we see today. Think of it like this: dark matter is the unseen architect, sketching the blueprints of the cosmos, while ordinary matter is the builder, filling in the details. Over time, gas and dust within these dark matter halos cooled and condensed, igniting the first stars and lighting up the universe. These early stars, in turn, produced heavier elements through nuclear fusion, enriching the cosmos with the building blocks for planets, life, and everything in between. Without dark matter's gravitational pull, none of this would have been possible. This cosmic dance between dark matter and ordinary matter has shaped the universe on the largest scales. Galaxy clusters, the largest structures in the universe, are held together by dark matter's immense gravitational influence. Even now, dark matter continues to guide the growth of cosmic structures, pulling galaxies together and shaping the cosmic web. It's a process that's been unfolding for over 13 billion years, creating the breathtaking tapestry of the universe we see today. Yet, while dark matter builds the universe, dark energy is quietly working to tear it apart. While dark matter's gravity pulls galaxies together, dark energy's repulsive force pushes them apart, accelerating the universe's expansion. It's a cosmic tug of war, with dark matter holding the universe together and dark energy driving it apart. This delicate balance between creation and destruction shapes the fate of the cosmos, determining how the universe will evolve over time. So, what does this mean for the future? As dark energy continues to accelerate the universe's expansion, will it eventually overcome dark matter's gravitational grip, scattering galaxies into oblivion? Or is there a balance we've yet to uncover? These are the questions that drive scientists to explore the universe's deepest mysteries, piecing together the story of how dark matter and dark energy shape everything we know and everything we don't. And as we continue this journey, one thing is clear: dark matter isn't just a ghostly presence in the cosmos, it's the architect of the universe, the invisible force that built the stage on which stars, planets, and galaxies perform. But how do we explore the unseen? How do we map the invisible threads that hold the universe together? That's where cutting-edge science and technology come into play, taking us to the next chapter in our cosmic quest. Dark energy isn't just an invisible force, it's the cosmic clock ticking away the fate of the universe. As it continues to accelerate the expansion of space, it raises profound questions about where everything is headed. One of the most widely discussed scenarios is the Big Freeze. Imagine a universe where galaxies drift farther and farther apart, their light stretched into invisibility as dark energy pushes them beyond the cosmic horizon. Over trillions of years, stars burn out, galaxies fade, and the universe grows colder and darker. It's a chilling vision of a future where the cosmos becomes a vast, empty void with no light, no heat, and no life. But the Big Freeze isn't the only possibility. There's also the Big Rip, a far more dramatic and destructive outcome. In this scenario, dark energy doesn't just push galaxies apart. It grows so strong that it tears apart everything in its path. First, galaxies are pulled apart, then stars, planets, and even atoms. Eventually, space itself is ripped apart at the seams, leaving behind a universe in shreds. It's a cosmic apocalypse, one where the very fabric of reality is destroyed by the relentless push of dark energy. What makes these scenarios possible is the nature of dark energy itself. Unlike gravity, which weakens with distance, dark energy's repulsive force seems to grow stronger as the universe expands. This means that over time, its influence becomes more dominant, overpowering even the gravitational pull of dark matter. It's a cosmic tug of war, with dark energy steadily gaining the upper hand. But here's the twist: not all scientists agree on how dark energy will behave in the future. Some theories suggest that dark energy might not be constant. It could change over time, becoming weaker or even reversing its effects. This opens the door to other possibilities, like a big crunch where the universe's expansion slows, stops, and eventually collapses back in on itself. Or perhaps dark energy could stabilize, leading to a more balanced cosmic future. The truth is, we don't yet know which path the universe will take. What we do know is that the interplay between dark matter and dark energy is crucial to the universe's fate. Dark matter's gravity builds the cosmic structures we see today, while dark energy's push threatens to unravel them. It's a delicate balance, one that has shaped the universe for billions of years and will continue to shape it for billions more. As we ponder these dramatic possibilities, one thing becomes clear: dark energy is more than just a mysterious force. It's the key to understanding the ultimate destiny of the cosmos. Whether the universe ends in a big freeze, a big rip, or something entirely unexpected, the story of dark energy is far from over. And as we continue to explore its secrets, we uncover not just the fate of the universe, but the profound connections between its invisible forces. So, what's next in this cosmic journey? How do we explore the interplay between dark matter and dark energy on the largest scales, and what might their balance or imbalance mean for the future of everything we know? The answers to these questions could redefine our understanding of the universe itself. The universe is a stage where two invisible giants are locked in an eternal tug of war, dark matter pulling, dark energy pushing, each shaping the cosmos in its own way. Picture this as a cosmic seesaw where dark matter's gravitational grip tries to hold everything together, while dark energy's relentless push works to tear it all apart. This delicate balance has defined the universe's evolution, from its fiery infancy to the vast expanse we see today. In the early universe, just moments after the Big Bang, dark matter had the upper hand. Its gravitational pull began to gather particles into dense clumps, creating the seeds for galaxies and galaxy clusters. Ordinary matter, the stuff of stars and planets, followed this dark matter blueprint, collapsing into these regions to ignite the first stars. For billions of years, dark matter's gravity dominated, weaving the cosmic web and building the intricate structures we observe today. But as the universe expanded, something shifted. Dark energy, once a faint whisper, began to grow stronger. Think of it like a cosmic counterweight, gradually tipping the seesaw in its favor. This mysterious force doesn't just push galaxies apart, it accelerates the expansion of space itself, stretching the fabric of the cosmos faster and faster over time. The result, a universe where galaxies are drifting farther apart, their light stretched into invisibility as dark energy's influence grows. This cosmic tug of war isn't static, it's a dynamic battle that's been unfolding for over 13 billion years. In the early universe, dark matter's gravity reigned supreme, pulling galaxies together and shaping the cosmic web. But as the universe grew larger and emptier, dark energy began to take over, its repulsive force becoming more dominant. Today, dark energy accounts for nearly 70% of the universe's total energy, while dark matter makes up about 25%, the remaining 5%. That's everything we can see, stars, planets, and all the luminous matter that fills the night sky. What's fascinating is how this balance has shifted over time. In the universe's youth, dark matter's gravity was the driving force, pulling matter together and creating the structures we see today. But as the cosmos expanded, dark energy began to take the lead, pushing galaxies apart and accelerating the universe's growth. It's like a cosmic game of tug-of-war, where the rope is constantly being pulled in different directions, with dark matter and dark energy each taking turns to dominate. But what does this mean for the future? Will dark energy's push eventually overcome dark matter's pull, scattering galaxies into oblivion? Or could the balance shift again, leading to new and unexpected outcomes? These are the questions that drive scientists to explore the universe's deepest mysteries, using every tool at their disposal to unravel the secrets of dark matter and dark energy. As we continue this cosmic journey, one thing is clear: the interplay between dark matter and dark energy isn't just a scientific curiosity, it's the story of the universe itself. From its earliest moments to its ultimate fate, these invisible forces shape everything we know and everything we don't. And as we delve deeper into their mysteries, we uncover not just the history of the cosmos, but the profound connections between its invisible architects. So, how do we explore this cosmic seesaw? What tools do we use to measure the invisible forces shaping the universe? From gravitational lensing to supernova observations, scientists are piecing together the story of dark matter and dark energy, one clue at a time. And as we continue to probe the cosmos, we uncover new layers of this cosmic dance, a dance that holds the key to understanding the universe's past, present, and future. Let's take a journey through time, a cosmic timeline that reveals how dark matter and dark energy have shaped the universe from its fiery beginnings to the vast expanse we see today. In the early moments after the Big Bang, the universe was a seething cauldron of particles, energy, and radiation. It was here, in this chaotic infancy, that dark matter began to exert its influence. While ordinary matter, the stuff of stars and planets, was buffeted by intense radiation, dark matter, unaffected by light, quietly began to clump together. These clumps acted like cosmic seeds, creating dense regions of gravitational pull that would eventually grow into galaxies and galaxy clusters. For billions of years, dark matter was the dominant force, weaving the cosmic web, a vast network of filaments connecting galaxies across the universe. Its gravitational pull drew matter together, igniting the first stars and lighting up the cosmos. Think of dark matter as the silent architect, sketching the blueprints for the universe's grand structures, while ordinary matter filled in the details. This era, often called the Dark Ages, was a time of creation where the building blocks of the universe were forged under dark matter's guiding hand. But as the universe expanded, something began to change. Around 5 billion years ago, dark energy, once a faint whisper in the cosmic background, started to make its presence known. Unlike dark matter, which pulls matter together, dark energy pushes it apart, acting as a kind of cosmic repulsion. As the universe grew larger and emptier, dark energy's influence became stronger, accelerating the expansion of space itself. This marked the beginning of a new era, one where dark energy began to take the lead. The transition from dark matter's dominance to dark energy's reign wasn't abrupt. It was a gradual shift, like the changing of seasons. For billions of years, dark matter's gravity had been the driving force behind the universe's growth. But as galaxies drifted farther apart, the effects of dark energy became more pronounced. Today, dark energy accounts for nearly 70% of the universe's total energy, while dark matter makes up about 25%, the remaining 5%. That's everything we can see: stars, planets, and all the luminous matter that fills the night sky. But how do we know this timeline is accurate? The evidence comes from a variety of sources. Observations of the cosmic microwave background, the afterglow of the Big Bang, reveal the early distribution of matter, showing how dark matter's gravitational pull shaped the universe's structure. Measurements of distant supernova, particularly Type Ia supernova, provide a record of the universe's expansion over time, highlighting the moment when dark energy began to dominate. And studies of galaxy clusters, the largest structures in the universe, show how dark matter's gravitational influence has evolved over billions of years. Together, this evidence paints a picture of a universe shaped by two invisible forces, one pulling, the other pushing, each taking turns to dominate. Dark matter laid the foundation, building the cosmic structures we see today, while dark energy is reshaping the universe, accelerating its expansion and determining its ultimate fate. This cosmic timeline isn't just a story of the past, it's a window into the future. As dark energy continues to push galaxies apart, what will become of the universe? Will it keep expanding forever, growing colder and darker, or could something unexpected change its course? These are the questions that drive scientists to explore the universe's deepest mysteries, piecing together the story of how dark matter and dark energy have shaped everything we know and everything we don't. And as we continue to unravel this cosmic tale, one thing becomes clear: the universe is far from static. It's a dynamic, ever-changing entity, shaped by forces we can't see but can't ignore. From its fiery beginnings to its uncertain future, the story of dark matter and dark energy is the story of the universe itself, a story that's still being written, one discovery at a time. The cosmic microwave background, or CMB, is like a time capsule from the universe's infancy, a faint glow that carries echoes of the Big Bang itself. Discovered by accident in the 1960s, this ancient light has become one of the most powerful tools for understanding the cosmos. It's the oldest light we can see, dating back to just 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. But the CMB isn't just a relic of the past, it's a treasure trove of clues about dark matter and dark energy, revealing how these invisible forces shaped the universe from the very beginning. When we look at the CMB, what we're seeing are tiny temperature fluctuations, slight variations in the heat of the early universe. These fluctuations might seem random at first glance, but they're actually a cosmic fingerprint, a map of the density variations that existed when the universe was young. Dark matter played a crucial role here. Its gravitational pull amplified these tiny ripples, creating denser regions that would eventually collapse to form galaxies and galaxy clusters. Without dark matter's influence, the universe might have remained smooth and featureless, a cosmic blank canvas. But the CMB doesn't just tell us about dark matter, it also holds clues about dark energy. One of the most striking features of the CMB is its large-scale structure. The way the temperature fluctuations are distributed across the sky reveals how the universe has expanded over billions of years. Dark energy, with its repulsive force, has been driving this expansion, stretching the fabric of space and influencing how these fluctuations appear today. By studying the CMB, scientists can measure the universe's expansion rate and track how dark energy's influence has grown over time. The CMB is like a cosmic puzzle, with each temperature fluctuation acting as a piece that fits into a larger picture. Missions like the Planck satellite have mapped these fluctuations with incredible precision, providing a detailed snapshot of the early universe. These maps show how dark matter's gravity pulled matter together to create the first structures, while dark energy's push began to counteract that pull, shaping the universe's evolution. Together, these invisible forces left their mark on the CMB, offering us a glimpse into the early moments of cosmic history. But the CMB isn't the only piece of evidence we have. Observations of distant supernova, galaxy clusters, and the large-scale structure of the universe all complement what we've learned from the CMB. Each of these tools provides a different perspective, helping us piece together the story of dark matter and dark energy. As we continue to explore these mysteries, one thing is certain. The CMB has given us a window into the universe's past, revealing the invisible forces that have shaped everything we see and everything we don't. And as we turn our attention to other observational evidence, we uncover even more layers of this cosmic story. From the bending of light around massive objects to the way galaxies rotate, each clue brings us closer to understanding the true nature of dark matter and dark energy. The journey is far from over, but with every discovery, we're getting closer to unraveling the secrets of the universe itself. Galaxy clusters are like cosmic laboratories, offering scientists a front-row seat to observe the invisible forces shaping our universe. These colossal structures, made up of hundreds or even thousands of galaxies bound together by gravity, are some of the largest and most massive objects in existence. But what makes them so fascinating isn't just their size, it's what they reveal about dark matter and dark energy. Take the Bullet Cluster, for example. This pair of colliding galaxy clusters is one of the most compelling pieces of evidence for dark matter's existence. When these clusters collided, the hot gas within them, visible in X-rays, slowed down and piled up in the center like two clouds merging. But something strange happened. The galaxies themselves, along with something invisible, kept moving forward unaffected by the collision. This invisible component. That's dark matter. Its gravitational effects, detected through gravitational lensing, showed that it passed right through the collision, leaving the gas behind. It's like watching two crowds of people walk through each other, but only the shadows keep moving. This observation provided direct proof that dark matter exists and behaves differently from ordinary matter. But galaxy clusters don't just reveal dark matter's presence. They also help us understand dark energy. By measuring how these clusters move and grow over time, scientists can track the universe's expansion rate. Dark energy, with its repulsive force, pushes galaxies apart, accelerating the expansion. In galaxy clusters, this effect is seen in the way their structures evolve. As dark energy becomes more dominant, it makes it harder for new clusters to form, slowing down the growth of cosmic structures. It's like trying to build a sandcastle while the tide is rising. Eventually, the waves win. However, studying galaxy clusters isn't without its challenges. Measuring their mass, for instance, requires precise observations of gravitational lensing and the motion of galaxies within them. And because dark energy's effects are subtle, detecting its influence requires mapping vast regions of the universe, often spanning billions of light years. It's a painstaking process requiring cutting-edge telescopes and sophisticated computer models to piece together the clues. Yet, despite these challenges, galaxy clusters remain one of our best tools for uncovering the secrets of dark matter and dark energy. They're cosmic time capsules, preserving the history of the universe's evolution and offering glimpses into the invisible forces that govern it. As we continue to study these massive structures, we uncover new insights into the nature of the cosmos and the delicate balance between its invisible giants. And as we move from the vast scales of galaxy clusters to the tiniest particles in the universe, we'll explore how scientists are searching for dark matter and dark energy on a microscopic level. What could these invisible forces be made of, and how might their discovery change our understanding of reality itself? That's where our journey takes us next. Studying something you can't see, touch, or directly detect might sound like science fiction, but for researchers exploring dark matter and dark energy, it's an everyday challenge. Imagine trying to solve a puzzle where most of the pieces are invisible. You can only see the shadows they cast. That's the reality scientists face as they work to unravel these cosmic mysteries. Despite decades of research, dark matter and dark energy remain elusive, detected only through their effects on the universe around them. It's a bit like trying to study the wind by watching how it moves the leaves. You can't see the wind itself, but you know it's there. One of the biggest hurdles is the lack of direct detection. Unlike stars, planets, or even black holes, dark matter and dark energy don't emit, absorb, or reflect light. They're completely invisible to our telescopes and instruments. This means scientists have to rely on indirect evidence, subtle clues like the way galaxies rotate, how light bends around massive objects, or how the universe's expansion accelerates over time. Each clue is like a breadcrumb, leading us closer to understanding these invisible forces, but the path is far from straightforward. To make matters more complex, the tools needed to study dark matter and dark energy are some of the most advanced ever created. Think of the Large Hadron Collider, a massive particle smasher designed to recreate conditions from the early universe, or the Hubble Space Telescope, peering billions of light years into the cosmos to measure the faint glow of distant supernova. These instruments are marvels of engineering, but they're also incredibly expensive and time-consuming to build and operate. And even with these tools, the search for dark matter and dark energy is like looking for a needle in a cosmic haystack. Adding to the challenge is the interdisciplinary nature of this field. Studying dark matter and dark energy isn't just about astronomy. It's a blend of physics, cosmology, and even philosophy. Physicists hunt for particles that could make up dark matter. Cosmologists map the large-scale structure of the universe to track dark energy's influence, and astronomers observe distant galaxies to piece together the cosmic puzzle. It's a collaborative effort, with scientists from different fields bringing their expertise to the table. But this also means progress can be slow, as breakthroughs often require new technologies, fresh perspectives, and a lot of patience. Beyond the scientific challenges, there's a deeper, almost philosophical question at the heart of this research. What does it mean that most of the universe is invisible to us? We've built our understanding of reality on what we can see and measure, but dark matter and dark energy remind us that there's so much more out there, forces and phenomena that defy our current understanding. It's humbling but also exhilarating, as every new discovery pushes the boundaries of what we know and opens up new questions to explore. So, as we continue to probe these cosmic mysteries, we're not just searching for answers about dark matter and dark energy, we're also redefining our place in the universe. What does it mean to live in a cosmos dominated by forces we can't see? And how might uncovering their secrets change the way we see ourselves and the world around us? These are the questions that drive scientists forward, fueling a quest that's as much about understanding the universe as it is about understanding ourselves. And as we dive deeper into these mysteries, we'll explore how cutting-edge technology and innovative theories are helping us push the boundaries of what's possible. From underground detectors to space telescopes, the tools of modern science are bringing us closer than ever to uncovering the secrets of the invisible universe. But the journey is far from over, and every discovery brings us one step closer to answering the ultimate question: what truly governs the cosmos? The discovery of dark matter and dark energy doesn't just reshape our understanding of the universe, it challenges the very way we think about reality itself. For centuries, humanity has looked to the stars and believed that what we see is all there is. But now we know better. The cosmos is far stranger and more mysterious than we ever imagined, with the vast majority of it hidden from our view. This realization forces us to confront profound questions. What does it mean to live in a universe where most of what exists is invisible to us? And how do we make sense of a reality where the rules we thought we understood only apply to a tiny fraction of the whole? At its core, this discovery is a humbling reminder of how much we still have to learn. For all our technological advancements and scientific breakthroughs, we've only scratched the surface of the universe's secrets. Dark matter and dark energy remind us that the cosmos operates on scales and in ways that defy our everyday experiences. They challenge us to rethink our assumptions about gravity, space, and even the nature of existence itself. It's a bit like standing on the shore of an ocean, realizing that what we've been calling the sea is just the foam on the waves. There's an entire world beneath the surface, vast and unexplored. This shift in perspective has cultural and philosophical implications that stretch far beyond science. Throughout history, humanity has often seen itself as the center of creation, the pinnacle of existence. But dark matter and dark energy remind us that we're not the main characters in this cosmic story. Instead, we're small, fleeting observers in a universe dominated by forces we can't see or fully understand. This realization can be unsettling, but it's also liberating. It invites us to embrace curiosity, to ask questions, and to marvel at the sheer scale and complexity of the cosmos. These invisible forces have also inspired new ways of thinking about art, literature, and even spirituality. The idea that most of the universe is hidden resonates with themes of mystery and wonder found in countless stories and traditions. From ancient myths about unseen worlds to modern science fiction exploring alternate dimensions, humanity has always been fascinated by the idea that there's more to reality than meets the eye. Dark matter and dark energy bring that idea into the realm of science, giving us a framework to explore the unknown in ways that blend imagination with rigorous inquiry. Yet, for all the questions they raise, dark matter and dark energy also offer a sense of connection. They remind us that the universe is a dynamic, ever-changing place, shaped by forces that stretch across unimaginable distances and timescales. In a way, they link us to the cosmos, showing that even the smallest parts of existence, like the atoms in our bodies, are part of a much larger story. It's a story that's still being written, one discovery at a time, and we're all part of it. As we reflect on these philosophical and cultural implications, one thing becomes clear. The study of dark matter and dark energy isn't just about uncovering the secrets of the universe, it's about understanding our place within it. It's a journey that challenges us to think bigger, to ask deeper questions, and to embrace the unknown with humility and wonder. And as we continue this journey, we'll explore how the tools of modern science are bringing us closer than ever to unraveling these cosmic mysteries, and what that means for the future of discovery itself. Dark matter and dark energy aren't just the subjects of scientific research, they've also captured the imagination of storytellers, artists, and creators around the world. From blockbuster movies to best-selling novels, these invisible forces have become a source of inspiration, sparking creativity and curiosity about the mysteries of the cosmos. Take Christopher Nolan's Interstellar, for example. The film dives deep into the complexities of gravity, time dilation, and the vastness of space, weaving in themes of humanity's place in a universe governed by forces we're only beginning to understand. While it doesn't explicitly name dark matter or dark energy, the film's portrayal of cosmic phenomena taps into the same sense of wonder and mystery that surrounds these invisible giants. Then there's Blake Crouch's novel Dark Matter, a sci-fi thriller that explores parallel universes and the infinite possibilities of existence. While the story leans more into quantum mechanics, its title alone reflects the cultural fascination with the unseen and the unknown. The idea of dark matter, something invisible yet omnipresent, serves as a metaphor for the hidden layers of reality that we're constantly trying to uncover. It's a reminder that the mysteries of the universe aren't just scientific, they're deeply human, tapping into our innate desire to explore, understand, and imagine what lies beyond the limits of our perception. This fascination with the unknown isn't limited to science fiction. Artists, too, have drawn inspiration from the enigmatic nature of dark matter and dark energy. Visual artists experiment with abstract forms and textures to evoke the unseen forces shaping the cosmos, while musicians compose soundscapes that echo the vastness and mystery of space. Even video games like No Man's Sky incorporate the awe-inspiring scale of the universe, inviting players to explore galaxies and phenomena that mirror the real-life mysteries scientists are grappling with. What ties all these creative expressions together is the sense of awe and wonder that dark matter and dark energy inspire. They represent the ultimate unknowns, the questions we're still trying to answer. And in that uncertainty lies a powerful source of inspiration, one that drives both artists and scientists to push boundaries, challenge assumptions, and explore new frontiers. But while popular culture thrives on imagination and speculation, the scientific community is hard at work turning these mysteries into knowledge. The same questions that fuel creative works: what is dark matter? What drives dark energy are the ones driving cutting-edge research. From underground detectors searching for elusive particles to space telescopes mapping the cosmos, scientists are piecing together the puzzle of these invisible forces, one observation at a time. This interplay between creativity and discovery is what makes the story of dark matter and dark energy so compelling. It's not just about the science or the art, it's about the human drive to explore the unknown, whether through equations or storytelling. And as we continue to unravel these cosmic mysteries, we're reminded that the universe is as much a source of inspiration as it is a subject of study. So, how is the scientific community tackling these questions? What tools and technologies are they using to peer into the invisible? From particle colliders to cosmic observatories, the search for answers is as bold and innovative as the stories they inspire. And as we shift our focus to these efforts, we'll see how science is turning the unknown into the known, one discovery at a time. The search for dark matter and dark energy isn't just a scientific endeavor, it's a global mission, uniting researchers, institutions, and nations in a shared quest to unravel the cosmos. From massive underground laboratories to cutting-edge space telescopes, this effort spans continents and disciplines, driven by a collective curiosity about the universe's deepest mysteries. At the heart of this collaboration is CERN, the European Organization for Nuclear Research, home to the Large Hadron Collider. Here, scientists smash particles at nearly the speed of light, recreating conditions from the early universe in hopes of producing, or at least detecting, dark matter particles. It's a monumental effort, one that combines physics, engineering, and computational power on an unprecedented scale. But the hunt for dark energy is equally ambitious. Projects like the Dark Energy Survey and the Euclid mission are mapping the universe in extraordinary detail, tracking billions of galaxies to measure how dark energy has influenced cosmic expansion over time. The Dark Energy Survey, for instance, uses a massive telescope in Chile to capture the light of distant galaxies, while Euclid, a European Space Agency mission, will peer even deeper into the cosmos, mapping the distribution of galaxies and dark matter across 10 billion light-years. These projects aren't just about collecting data, they're about creating a cosmic map, one that reveals the invisible forces shaping the universe. Behind these groundbreaking missions lies another unsung hero: supercomputers. The sheer volume of data generated by these projects is staggering. Billions of galaxies, trillions of data points, all of which need to be processed, analyzed, and interpreted. Supercomputers like those at the National Center for Supercomputing Applications in the U.S. or the DI-RSC facility in the U.K. are essential for simulating the universe, running complex models that recreate cosmic evolution over billions of years. These simulations allow scientists to test theories, predict outcomes, and compare their results to real-world observations, bridging the gap between theory and reality. Of course, none of this would be possible without funding and public support. Projects like CERN, the Dark Energy Survey, and Euclid require billions of dollars, years of planning, and the collective effort of thousands of scientists, engineers, and technicians. Governments, private institutions, and even citizen scientists all play a role in making these missions a reality. Public outreach and education are also crucial, helping to inspire the next generation of researchers and ensure that the quest to understand the cosmos continues. Looking to the future, the possibilities are as vast as the universe itself. Upcoming missions like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope promise to push the boundaries even further, offering new insights into dark matter and dark energy. Meanwhile, advancements in technology and computing power are opening up entirely new ways to explore these invisible forces. From quantum sensors to artificial intelligence, the tools of tomorrow may finally bring us face to face with the cosmic ghosts that have eluded us for so long. This global effort isn't just about answering scientific questions, it's about expanding the horizons of human knowledge. As we continue to explore the mysteries of dark matter and dark energy, we're not just uncovering the secrets of the universe, we're redefining what it means to explore, to discover, and to understand our place in the cosmos. And as we turn our gaze to the future, one thing is certain: the journey is far from over, and the next breakthrough could be just around the corner. The future of cosmology is brimming with promise as new missions and experiments prepare to take us deeper into the mysteries of dark matter and dark energy than ever before. One of the most anticipated projects is the Vera Rubin Observatory, set to begin operations in the mid-2020s. This state-of-the-art facility, equipped with the world's largest digital camera, will scan the entire southern sky every few nights, capturing an unprecedented amount of data. Its goal: to map billions of galaxies, track the distribution of dark matter, and measure how dark energy has influenced the universe's expansion over billions of years. It's like giving the cosmos a massive CT scan, revealing the hidden structures and forces that shape everything we see. But the Vera Rubin Observatory isn't the only game changer on the horizon. The James Webb Space Telescope, already revolutionizing our view of the cosmos, is set to play a pivotal role in understanding dark matter and dark energy. By peering into the earliest moments of the universe, Webb can help us study the formation of the first galaxies and how dark matter influenced their growth. Its infrared capabilities also allow it to observe distant supernova and galaxy clusters with unparalleled detail, shedding new light on how dark energy has driven the universe's accelerating expansion. Together, these observatories represent a new era of discovery, offering tools so powerful they could rewrite our understanding of the cosmos. What makes these missions so exciting is their potential to answer questions that have puzzled scientists for decades. For instance, could dark matter and dark energy be two sides of the same cosmic coin? Some theorists propose that a single, unified theory might explain both phenomena, linking them in ways we've yet to imagine. This idea, often referred to as unified dark sector models, suggests that dark matter and dark energy might not be separate entities but different manifestations of a single underlying force. It's a bold idea, one that could simplify our understanding of the universe and reveal connections we've overlooked. Of course, not everyone is convinced that dark matter and dark energy are the only explanations. Some scientists are exploring alternative theories like modified Newtonian dynamics or MUND, which suggests that our understanding of gravity might need tweaking on cosmic scales. Others propose that dark energy could be a dynamic field, changing over time and interacting with other forces in ways we don't yet understand. These alternatives challenge the status quo, pushing us to think outside the box and consider new possibilities. As we stand on the brink of this new era in cosmology, one thing is clear: the next decade could bring breakthroughs that reshape our understanding of the universe. From groundbreaking observations to bold new theories, the search for answers is more exciting than ever. And as we continue to explore these mysteries, we're not just uncovering the secrets of dark matter and dark energy, we're rewriting the story of the cosmos itself. So, what will these discoveries mean for our understanding of reality? Could we be on the verge of uncovering a unified theory that ties everything together? Or might we uncover something entirely unexpected, forcing us to rethink what we thought we knew? These are the questions that drive scientists forward, fueling a quest that's as much about understanding the universe as it is about understanding ourselves. And as we turn our gaze to the future, one thing is certain: the journey is far from over, and the next chapter in this cosmic story promises to be the most thrilling yet. While dark matter and dark energy have become the leading explanations for the universe's behavior, not everyone is convinced they're the full story. Some scientists are exploring alternative theories that challenge the status quo, offering fresh perspectives on the cosmic mysteries we're still trying to solve. One of the most debated alternatives is modified Newtonian dynamics, or MUND. Proposed in the early 1980s by physicist Mordechai Milgrom, MUND suggests that our understanding of gravity might be incomplete, especially on the vast scales of galaxies and galaxy clusters. Instead of invoking dark matter, MUND proposes that gravity behaves differently at extremely low accelerations like those found at the edges of galaxies. This tweak to Newton's laws could explain why stars on the outskirts of galaxies move faster than expected without needing invisible matter. At first glance, MUND seems like an elegant solution. It accounts for the observed motion of stars in galaxies without requiring dark matter, and it's been surprisingly successful at predicting galactic rotation curves. But MUND isn't without its challenges. While it works well for individual galaxies, it struggles to explain the behavior of galaxy clusters and the large-scale structure of the universe. For example, when galaxy clusters collide, the way their mass is distributed, including the separation of gas and dark matter, can't be fully explained by modified gravity alone. This has led many scientists to view MUND as an incomplete theory, one that might need additional components to match all the observations. Another intriguing alternative is emergent gravity, a theory proposed by physicist Eric Verland in 2010. Unlike MUND, which modifies Newton's laws, emergent gravity suggests that gravity isn't a fundamental force at all. Instead, it's an emergent phenomenon, a side effect of the way information is distributed across the universe. In this view, dark matter isn't a particle or substance. It's a manifestation of the way space-time itself behaves on large scales. Emergent gravity has gained attention for its bold reimagining of gravity, but like MUND, it faces significant hurdles. Critics argue that it struggles to explain certain observations, such as the precise details of galaxy rotation curves or the cosmic microwave background. These alternative theories highlight an important truth: science thrives on questioning and debate. While dark matter and dark energy remain the most widely accepted explanations, MUND and emergent gravity remind us that there's always room for new ideas. They challenge us to think differently, to question our assumptions, and to explore whether the universe might operate in ways we haven't yet imagined. But here's the catch: none of these alternatives have been able to fully replace dark matter and dark energy. Each has its strengths, but they also have gaps that keep them from being universally accepted. This ongoing debate is a testament to the complexity of the cosmos and to the creativity of the scientists trying to unravel its secrets. So, what does this mean for the central question: what is really in control of the universe? Whether it's dark matter and dark energy, modified gravity, or something entirely new, the answer isn't set in stone. The universe is full of surprises, and the tools we're using to explore it, from particle colliders to space telescopes, are revealing new layers of complexity every day. As we continue this journey, one thing is certain: the search for answers is far from over, and the next breakthrough could come from anywhere or anyone. And as we turn our attention to the tools and technologies driving this search, we'll see how cutting-edge science is bringing us closer than ever to understanding the invisible forces that shape our universe. From underground experiments to cosmic observatories, the quest to uncover the truth is as exciting as it is challenging, and the discoveries ahead could change everything we think we know. So here we are, standing at the crossroads of cosmic understanding, staring into the vastness of a universe ruled by two invisible giants. Dark matter, with its gravitational grip, holds galaxies together, stitching the cosmos into a web of structure. Dark energy, on the other hand, is the cosmic rebel, pushing the universe apart with a force that grows stronger as space expands. Together, they shape everything from the smallest galaxies to the largest scales of existence. But which one is truly in control of the universe? Let's start with dark matter. Its influence is undeniable. Without it, galaxies would fly apart, their stars scattering into the void. We see its effects everywhere: in the way galaxies rotate, how light bends around massive objects, and even in the faint echoes of the Big Bang. Dark matter is the cosmic architect, the unseen hand that built the universe's grand structures. It's been the dominant force for billions of years, pulling matter together and giving shape to everything we see. But dark energy is no less powerful. Though it only became significant in the last 5 billion years, its impact is profound. As the universe expanded, dark energy's repulsive force grew stronger, accelerating the cosmos's growth. Today, it accounts for nearly 70% of the universe's total energy, making it the dominant force on the largest scales. Dark energy is the cosmic clock, ticking away the fate of the universe, pushing galaxies apart faster and faster. The interplay between these two forces is a delicate dance. Dark matter builds the universe, creating the structures we see today, while dark energy reshapes it, accelerating its expansion and dictating its ultimate fate. But here's the big question: will this balance last? Could one force eventually overcome the other? If dark energy continues to dominate, the universe could face a big freeze, a future where galaxies drift so far apart that they vanish from view, leaving the cosmos cold, dark, and empty. Alternatively, if dark energy grows even stronger, it might trigger a big rip, tearing apart galaxies, stars, and even atoms. On the other hand, if dark matter's gravitational pull somehow regains the upper hand, the universe could slow its expansion, potentially leading to a big crunch or collapse back into a single point. But these scenarios aren't just speculative, they're tied to fundamental questions about the nature of reality. Could dark matter and dark energy be two sides of the same cosmic coin? Some theories suggest they might be connected, part of a unified framework that explains both phenomena. Others propose that our understanding of gravity itself might need revising, pointing to alternative theories like Mund or emergent gravity. This isn't just about predicting the universe's fate, it's about understanding the laws that govern it. Dark matter and dark energy challenge our most fundamental assumptions about physics, forcing us to rethink everything from gravity to the nature of space and time. Each new discovery brings us closer to answers, but also raises new questions, keeping the cosmic puzzle as intriguing as ever. So, as we ponder which force, dark matter or dark energy, holds the reins of the cosmos, we're reminded that the universe is far more complex than we often assume. It's a dynamic, ever-changing entity shaped by forces we can't see but can't ignore. And as we continue to explore these mysteries, we're not just uncovering the secrets of the universe, we're rewriting the story of reality itself. What does this mean for the future of physics? Could the answers lie in a unified theory that ties everything together, or might we uncover something entirely unexpected? These are the questions that drive scientists forward, fueling a quest that's as much about understanding the universe as it is about understanding ourselves. And as we turn our gaze to the next chapter in this cosmic journey, one thing is certain: the search for answers is far from over, and the discoveries ahead could change everything we think we know. Dark matter and dark energy aren't just cosmic mysteries. They're a direct challenge to the very foundations of modern physics. For decades, the standard model of particle physics has been our best framework for understanding the universe's building blocks, from quarks to electrons. It's a theory that's incredibly successful, predicting the behavior of particles with astonishing precision. But here's the catch: the standard model doesn't account for dark matter or dark energy. In fact, it leaves them entirely unexplained, and that's a problem. The same goes for Einstein's theory of general relativity, which describes gravity as the curvature of spacetime. While it's been remarkably accurate in explaining everything from black holes to the bending of light, general relativity doesn't provide answers for dark energy's accelerating expansion of the universe. This gap between theory and observation has forced physicists to rethink their assumptions. Could the standard model and general relativity be incomplete? And if so, what comes next? This is where the idea of a new paradigm comes in. Scientists are searching for a theory of everything, a single framework that unites all the forces of nature, from gravity to quantum mechanics, and explains phenomena like dark matter and dark energy. It's a daunting task, but it's also one of the most exciting areas of research in modern physics. One promising avenue is quantum gravity, which seeks to reconcile general relativity with quantum mechanics. In the quantum world, particles behave in strange, unpredictable ways, governed by probabilities rather than fixed laws. But when it comes to gravity, quantum mechanics falls short. Quantum gravity aims to bridge this gap, offering a way to describe gravity at the smallest scales. Some theories, like loop quantum gravity, propose that spacetime itself is made up of tiny, discrete loops, while others suggest that gravity emerges from quantum entanglement. These ideas are still in their infancy, but they could hold the key to understanding dark matter and dark energy. Another contender is string theory, which posits that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in higher dimensions, creating the particles and forces we observe in our three-dimensional world. String theory offers a potential way to unify all the forces of nature, including gravity, and could even explain dark matter and dark energy as manifestations of these higher dimensional strings. But string theory is notoriously complex, and it's yet to make testable predictions that could confirm its validity. The search for a new paradigm isn't just about filling in the gaps, it's about reimagining our understanding of reality. What if dark matter and dark energy aren't separate phenomena but part of a larger, unified framework? Some theories propose that dark matter could be made up of particles predicted by supersymmetry, a theory that extends the standard model by suggesting every known particle has a heavier superpartner. Others suggest that dark energy might be linked to the vacuum energy of space, a concept rooted in quantum field theory. These ideas aren't just abstract musings, they're driving real-world experiments. From particle colliders like the Large Hadron Collider to space telescopes mapping the cosmic microwave background, scientists are testing these theories with cutting-edge technology. Each experiment brings us closer to understanding whether dark matter and dark energy can be explained within our current frameworks, or if we need a completely new way of thinking about the universe. The implications of this quest go far beyond physics. Discovering a new paradigm could revolutionize our understanding of everything from the Big Bang to the fate of the cosmos. It could redefine our place in the universe, showing us that the forces we once thought were separate are actually part of a deeper, more interconnected reality. So, as we continue to explore these invisible giants, we're not just chasing answers, we're rewriting the rules of science itself. What could this new paradigm look like? And how might it change the way we see the universe? The answers to these questions could reshape our understanding of reality, opening up new frontiers of discovery that we've only begun to imagine. And as we turn our attention to the broader implications of this research, we'll see how the study of dark matter and dark energy isn't just about physics, it's about expanding the horizons of human knowledge and redefining what it means to explore the cosmos. The mysteries of dark matter and dark energy aren't just scientific puzzles, they're gateways to a deeper understanding of the universe itself. Solving these enigmas could revolutionize not only cosmology, but also our grasp of fundamental physics, reshaping everything from the smallest particles to the largest cosmic structures. Imagine the possibilities, a unified theory that ties together gravity, quantum mechanics, and the forces of nature, explaining phenomena that have baffled us for decades. This isn't just about filling in gaps, it's about rewriting the rules of reality. One of the most exciting prospects is the potential for new technologies. Historically, breakthroughs in physics have led to transformative innovations. Quantum mechanics, for instance, gave us transistors and the digital age. Similarly, unraveling the secrets of dark matter and dark energy could unlock technologies we can barely imagine today. From new forms of energy to advanced propulsion systems for space exploration, the ripple effects of this research could extend far beyond the lab, shaping the future of humanity itself. But the impact goes even deeper. Understanding dark matter and dark energy could provide insights into the very fabric of space-time. Are we missing something fundamental about gravity? Could there be hidden dimensions or undiscovered particles waiting to be found? These questions push the boundaries of what we know, challenging us to rethink the foundations of physics. The pursuit of answers isn't just about solving cosmic mysteries, it's about expanding the frontiers of human knowledge. This quest is inherently interdisciplinary, bridging astronomy, particle physics, and cosmology. Astronomers map the large-scale structure of the universe, particle physicists search for elusive dark matter particles, and cosmologists model the universe's evolution. Together, these fields form a collaborative effort, pooling expertise to tackle questions no single discipline could answer alone. It's a reminder that science thrives on diversity of ideas, methods, and perspectives. Yet, as we push forward, it's essential to consider the ethical implications of this research. What responsibilities come with uncovering the universe's deepest secrets? Could new technologies derived from this knowledge be used for harm as well as good? And how do we ensure that the benefits of these discoveries are shared equitably across society? These are questions that go beyond science, touching on the moral and philosophical dimensions of exploration. As we continue to probe the mysteries of dark matter and dark energy, we're not just seeking answers, we're shaping the future of science and humanity. The journey is as much about the questions we ask as the answers we find, reminding us that the pursuit of knowledge is a deeply human endeavor. And as we turn our gaze to the next chapter in this cosmic story, one thing is certain: the discoveries ahead could change everything we think we know about the universe and our place within it. As we push the boundaries of our understanding, exploring the invisible forces that shape the universe, it's worth stepping back to ask, what are the ethical implications of this pursuit? The study of dark matter and dark energy isn't just a scientific endeavor. It's a human one with real-world consequences that extend far beyond the lab. From the allocation of resources to the potential for unintended consequences, these questions force us to consider not just what we can do, but what we should do in the name of discovery. First, let's talk about resource allocation. Research into dark matter and dark energy is expensive, requiring cutting-edge technology, massive collaborations, and years of effort. Projects like the Large Hadron Collider or the James Webb Space Telescope cost billions of dollars, raising questions about how we prioritize scientific exploration. Should we invest heavily in understanding the cosmos, or should these resources be redirected to address more immediate challenges like climate change, poverty, or global health? It's a complex balance, one that requires weighing the long-term benefits of discovery against the pressing needs of the present. But here's the thing: the pursuit of knowledge isn't a zero-sum game. Many of the technologies developed for cosmology, like advanced computing, imaging, and data analysis, have applications far beyond astronomy. For example, innovations from particle physics research have led to breakthroughs in medical imaging, while satellite technology has revolutionized communication and environmental monitoring. In this way, investing in dark matter and dark energy research isn't just about understanding the universe, it's about driving progress that benefits society as a whole. Then there's the question of unintended consequences. While the study of dark matter and dark energy is largely theoretical, the potential for discovery raises ethical dilemmas. What if, for instance, we uncover a new form of energy that could be weaponized? Or what if advancements in our understanding of gravity lead to technologies with unforeseen risks? These scenarios might sound like science fiction, but history is full of examples where scientific breakthroughs had both positive and negative impacts. The development of nuclear energy, for example, brought clean power but also the threat of atomic weapons. As we explore the unknown, we must remain vigilant, ensuring that our discoveries are used responsibly. This brings us to the role of public engagement. Science isn't conducted in a vacuum, it's a shared endeavor that thrives on collaboration and communication. By involving the public in the conversation, we can foster a sense of collective ownership over these discoveries. Public outreach programs, citizen science initiatives, and educational campaigns help demystify complex topics, making them accessible to everyone. When people understand the importance of dark matter and dark energy research, they're more likely to support it, ensuring that the pursuit of knowledge remains a communal effort. But public engagement isn't just about education, it's also about inclusion. The study of the cosmos should reflect the diversity of humanity, with voices from all backgrounds contributing to the conversation. By breaking down barriers and encouraging participation from underrepresented groups, we can ensure that the benefits of discovery are shared equitably and that the ethical questions we face are considered from multiple perspectives. In the end, the ethical considerations surrounding dark matter and dark energy research remind us that science isn't just about answering questions, it's about asking them. How do we balance curiosity with responsibility? How do we ensure that the pursuit of knowledge benefits everyone? These are questions without easy answers, but they're essential to the ongoing dialogue about our place in the universe. And as we turn our attention to the broader implications of this research, we'll see how the study of dark matter and dark energy isn't just about uncovering the secrets of the cosmos, it's about shaping the future of humanity itself. From the technologies we develop to the values we uphold, the choices we make today will echo far into the future, defining not just what we discover but who we become. The mysteries of dark matter and dark energy aren't just for scientists, they are for everyone. After all, the cosmos belongs to us all, and understanding its deepest secrets should be a shared journey. That's where science communication comes in, bridging the gap between complex research and the curiosity of the everyday person. From planetarium shows that light up the night sky with stunning visuals of the universe's invisible forces, to documentaries that dive deep into the latest discoveries, these tools bring the cosmos closer to home. They transform abstract concepts into tangible stories, sparking wonder and inspiring the next generation of explorers. Take planetariums, for example. These immersive spaces allow people to step into the universe, experiencing the scale and beauty of galaxies, dark matter filaments, and the accelerating expansion driven by dark energy. It's not just about dazzling visuals, it's about creating a connection, helping people see themselves as part of something much larger. Similarly, documentaries like Cosmos or The Elegant Universe break down complex ideas into digestible narratives, making the invisible forces shaping our universe feel real and relatable. But science communication isn't limited to screens and domed ceilings. Citizen science projects like Zooniverse invite everyone to participate in real research, from classifying galaxies to searching for signs of dark matter. These initiatives democratize discovery, showing that you don't need a PhD to contribute to our understanding of the cosmos. It's a powerful reminder that science is a collective effort, one that thrives on the curiosity and enthusiasm of people from all walks of life. And then there's social media, a tool that's revolutionized how we share knowledge. Platforms like YouTube have become hubs for science communication, with creators using animation, storytelling, and even humor to explain everything from gravitational lensing to the nature of dark energy. Channels like PBS Space-Time and Kurzgesagt make the cosmos accessible to millions, breaking down barriers and fostering a global community of curious minds. Social media also allows for real-time engagement, letting people ask questions, share insights, and feel personally connected to the discoveries being made. But why does this matter? Beyond the awe and wonder, these efforts have a profound personal impact. Learning about dark matter and dark energy isn't just about understanding the universe, it's about understanding ourselves. It's a reminder of our place in the cosmos, of how much we've learned and how much more there is to discover. It's about sparking curiosity, inspiring creativity, and showing that the pursuit of knowledge is a deeply human endeavor. As we continue to explore these invisible giants, science communication ensures that their stories reach far beyond the lab, touching hearts and minds around the world. And as we turn our attention to the future, one thing is clear. The more we share these discoveries, the more we inspire others to join the journey, ensuring that the quest to understand the cosmos remains a shared adventure. So, what does all this dark matter, dark energy, the invisible forces shaping the cosmos mean for you? It's easy to think of these topics as abstract, something confined to textbooks or distant galaxies. But the truth is, understanding the universe's composition has a profound personal impact. It's not just about science, it's about how these discoveries shape the way we see ourselves and the world around us. Think about it, every time you look up at the night sky, you're seeing a universe that's 95% invisible. That realization alone can spark a sense of awe, a reminder that there's so much more out there than meets the eye. It's humbling, sure, but also deeply inspiring. Contemplating the cosmos invites us to think bigger, to ask questions, and to embrace the unknown. Whether you're a casual stargazer or a lifelong space enthusiast, that sense of wonder is universal. And there's science to back this up. Studies have shown that contemplating the vastness of the universe can trigger what psychologists call the overview effect, a shift in perspective that fosters feelings of connectedness and humility. It's the same phenomenon astronauts describe when they see Earth from space, a profound realization that we're all part of something much larger. Even without leaving the planet, learning about dark matter and dark energy can give us a glimpse of that same perspective. It's a reminder that we're not just observers of the universe, we're participants in its grand story. This connection to the cosmos isn't just philosophical, it's practical too. The curiosity that drives scientists to explore dark matter and dark energy is the same curiosity that fuels innovation and creativity in everyday life. From technology to art, the questions we ask about the universe often lead to breakthroughs that shape our world. The same tools used to map the cosmic web or detect dark matter particles have applications in medicine, engineering, and beyond. In a way, the pursuit of cosmic understanding enriches not just our minds but our lives. But perhaps the most profound impact is how it changes the way we see ourselves. In a universe dominated by invisible forces, where galaxies are held together by dark matter and pushed apart by dark energy, our existence feels both fragile and extraordinary. It's a paradox that invites reflection. We're tiny in the grand scheme of things, yet capable of understanding and exploring the vastness around us. That duality, of being small yet significant, can be a source of both humility and empowerment. As we look back on the journey we've taken so far, from the discovery of dark matter to the mysteries of dark energy, it's clear that these invisible forces aren't just shaping the universe, they're shaping us. They challenge us to think differently, to stay curious, and to embrace the unknown. And in doing so, they remind us that the cosmos isn't just something out there, it's a part of who we are, woven into the fabric of our existence. So, what's next in this cosmic journey? How do we continue to explore these mysteries, and what might their answers reveal about our place in the universe? As we turn our attention to the future, one thing is certain. The quest to understand dark matter and dark energy isn't just about uncovering the secrets of the cosmos. It's about discovering what it means to be human in a universe full of wonder. So, let's take a moment to look back at the incredible journey we've taken through the invisible universe. We started with a simple but startling fact. The stars, planets, and galaxies we see make up just 5% of the cosmos. The rest, a vast hidden realm dominated by dark matter and dark energy, two mysterious forces that shape everything from the smallest galaxies to the largest cosmic structures. We trace the discovery of dark matter back to the 1930s, when Fritz Zwicky first noticed something strange about the motion of galaxies in the Coma cluster. Decades later, Vera Rubin's groundbreaking work on galaxy rotation curves confirmed that something invisible, something massive, was holding the universe together. From there, we explored how dark matter's gravitational pull acts like cosmic glue, bending light, shaping galaxies, and weaving the intricate web of the cosmos. Then came dark energy, the enigmatic force that flipped the script on our understanding of the universe's fate. In the late 1990s, observations of distant supernovae revealed that the universe isn't just expanding, it's accelerating. Dark energy, with its repulsive push, emerged as the dominant force on the largest scales, driving galaxies apart faster and faster. Together, dark matter and dark energy form a cosmic tug-of-war, one pulling, the other pushing, shaping the universe's past, present, and future. But the story doesn't end there. We've also explored the challenges of studying these invisible forces, how scientists use tools like gravitational lensing, supernova observations, and the cosmic microwave background to map their influence. We've delved into the cutting-edge experiments searching for dark matter particles, from underground detectors to particle colliders, and the ambitious space missions aiming to uncover dark energy's secrets. And yet, despite all we've learned, the mysteries remain. What is dark matter made of? Is it a new kind of particle or something we've yet to imagine? What drives dark energy? Is it a property of space itself or a sign of new physics? These questions are at the heart of modern cosmology, driving scientists to push the boundaries of what we know. As we stand on the brink of new discoveries, one thing is clear: the universe is far stranger and more complex than we ever imagined. Dark matter and dark energy aren't just scientific curiosities. They're the architects of the cosmos, shaping everything from the smallest galaxies to the vast expanse of space itself. And as we continue to explore their secrets, we're not just uncovering the story of the universe, we're rewriting it. So, what's next? What does the future hold for our understanding of the cosmos? Will we finally detect dark matter particles, unlocking the secrets of this cosmic ghost? Could new theories emerge, uniting dark matter and dark energy into a single, elegant framework? Or might we uncover something entirely unexpected, challenging everything we thought we knew? The journey to understand the invisible universe is far from over. With every discovery, every experiment, and every new question, we're getting closer to unraveling the mysteries that define our cosmos. And as we look to the future, one thing is certain: the adventure is just beginning. So, what do you think? What's the next big breakthrough in our understanding of the universe? Let's keep exploring, keep questioning, and keep marveling at the wonders of the cosmos. After all, the universe is full of surprises, and the best discoveries are yet to come. What does the future hold for the universe? It's a question that has captivated scientists and dreamers alike, and the answers hinge on the delicate balance between dark matter and dark energy. Based on what we know today, several scenarios emerge, each painting a different picture of the cosmos' ultimate fate. Let's start with the Big Freeze, also known as the heat death. In this scenario, dark energy continues to accelerate the universe's expansion, pushing galaxies farther and farther apart. Over trillions of years, stars will burn out, galaxies will fade, and the universe will grow colder and darker, eventually reaching a state of near-perfect stillness. It's a slow, quiet end, a cosmic fade to black, but the Big Freeze isn't the only possibility. There's also the Big Rip, a far more dramatic finale. If dark energy's repulsive force grows stronger over time, it could eventually overcome even the strongest forces holding matter together. Galaxies would be torn apart first, followed by stars, planets, and even atoms. Space itself would be ripped apart at the seams, leaving the universe in shreds. It's a violent, chaotic end, one that underscores the raw power of dark energy. Of course, these scenarios aren't set in stone. They're based on our current understanding of dark energy, which could change with new discoveries. What if dark energy isn't constant? What if it weakens over time or even reverses its effects? In that case, the universe's expansion could slow down, potentially leading to a big crunch, a collapse back into a single point, much like the Big Bang in reverse. It's a cyclical vision of the cosmos where the universe expands and contracts in an endless loop. Then there's the possibility of something entirely unexpected. Science thrives on surprises, and the history of cosmology is full of moments where new discoveries upended our assumptions. Could a breakthrough in our understanding of dark matter or dark energy reveal a completely different future? Perhaps dark energy isn't a force at all, but a sign of new physics waiting to be uncovered. The universe has a way of defying expectations, and the next big discovery could rewrite the cosmic forecast entirely. What ties all these possibilities together is the human quest for knowledge. For centuries, we've looked to the stars, seeking answers to the biggest questions. Where did we come from? What is our place in the cosmos, and where are we headed? Dark matter and dark energy are part of that story, two invisible giants that shape the universe's past, present, and future. As we continue to explore their mysteries, we're not just predicting the fate of the cosmos, we're uncovering the story of existence itself. And so, the journey continues. With every observation, every experiment, and every new theory, we're getting closer to understanding the forces that govern the universe. But the beauty of science lies in its unpredictability. The next discovery could change everything, revealing a universe far stranger and more wondrous than we ever imagined. As we look to the future, one thing is certain: the adventure is far from over, and the cosmos still has plenty of secrets to share. What do you think lies ahead? A cold, quiet end, a dramatic collapse, or something we haven't even dreamed of yet? The universe is full of surprises, and the next chapter in this cosmic story is waiting to be written. The universe is vast, mysterious, and filled with questions that have captivated humanity for centuries. From ancient civilizations gazing at the stars to modern scientists probing the depths of space, our quest to understand the cosmos is a timeless pursuit. It's a journey that transcends cultures, generations, and disciplines, driven by an insatiable curiosity to uncover the secrets of existence. And today, as we grapple with the enigmas of dark matter and dark energy, we're continuing this age-old tradition of exploration and discovery. What makes this quest so enduring? At its core, it's about more than just finding answers, it's about the thrill of the unknown. Every time we uncover a piece of the cosmic puzzle, new questions emerge, pushing us to dig deeper and think bigger. Dark matter and dark energy are the latest frontiers in this ongoing adventure, challenging us to rethink what we know about the universe and our place within it. They remind us that the cosmos is far more complex and wondrous than we ever imagined, and that the pursuit of knowledge is a journey without end. But this journey isn't one we take alone. The search for dark matter and dark energy is a collaborative effort uniting scientists, engineers, and thinkers from around the world. From massive particle colliders to space telescopes, these projects require the expertise of thousands working together to push the boundaries of what's possible. It's a testament to the power of human ingenuity and perseverance, showing that even the most daunting challenges can be overcome when we work as one. This spirit of collaboration extends beyond the lab. Public engagement and education play a crucial role in bringing the mysteries of the cosmos to life, inspiring the next generation of explorers. Whether it's through planetarium shows, citizen science projects, or viral YouTube videos, the story of dark matter and dark energy is being shared with millions, sparking curiosity and wonder in people of all ages. It's a reminder that the quest for knowledge is a shared endeavor, one that belongs to all of us. As we reflect on this legacy, it's impossible not to feel a sense of awe. The search for dark matter and dark energy is more than a scientific pursuit, it's a testament to humanity's resilience, creativity, and boundless curiosity. It's a story of how far we've come, from the first stargazers to the cutting-edge experiments of today, and a glimpse of what's yet to come. And so, as we look to the future, we carry forward this legacy of exploration, driven by the same questions that have inspired us for millennia. What lies beyond the stars? What forces shape the cosmos? And what does it all mean for us? These questions are the heartbeat of our journey, propelling us forward into the unknown. Because in the end, the quest for knowledge isn't just about finding answers, it's about discovering who we are and what we're capable of. What discoveries await us in the years to come? How will our understanding of dark matter and dark energy evolve? The answers are out there, waiting to be uncovered as we continue this timeless pursuit of understanding the universe and ourselves. The mysteries of dark matter and dark energy aren't just scientific puzzles, they're catalysts for a brighter, more curious future. Solving these enigmas could redefine how future generations see the cosmos, inspiring a new wave of scientists, engineers, and dreamers. Imagine a child today captivated by the idea of invisible forces shaping the universe. growing up to design experiments that finally detect dark matter or uncover the true nature of dark energy. These discoveries wouldn't just expand our knowledge, they'd ignite a spark of curiosity that could fuel innovation for decades to come. But the impact goes beyond science. Unlocking the secrets of dark matter and dark energy could lead to technological breakthroughs we can't yet imagine. Historically, solving big cosmic questions has often led to unexpected advancements. For instance, the quest to understand quantum mechanics gave us the foundation for modern computing. Similarly, the pursuit of these invisible giants could pave the way for new energy sources, advanced materials, or even revolutionary space travel technologies. It's a reminder that the journey to understand the universe often brings benefits that ripple far beyond the lab. Culturally and philosophically, these discoveries could spark a profound shift in how we see ourselves. If most of the universe is invisible, what does that say about our perception of reality? Could it inspire a new kind of humility, a recognition that there's always more to learn? At the same time, it might also fuel a sense of wonder and possibility, showing us that the cosmos is far stranger and more complex than we ever imagined. These ideas could reshape art, literature, and even spirituality, offering fresh ways to explore the big questions of existence. At the heart of all this is the role of imagination in science. Solving the mysteries of dark matter and dark energy requires more than just equations and experiments. It demands creativity. Scientists must imagine scenarios that defy everyday experience, from particles that barely interact with matter to forces that stretch the fabric of space itself. This blend of logic and imagination is what makes science so powerful and so human. It's a reminder that the pursuit of knowledge isn't just about finding answers, it's about daring to ask questions that challenge our understanding of reality. As we look to the future, one thing is clear: the legacy of dark matter and dark energy research isn't just about what we discover, it's about the journey itself. It's about inspiring curiosity, pushing boundaries, and redefining what's possible. And as we continue to explore these invisible forces, we're not just shaping the future of science, we're shaping the future of humanity. So, what's next in this cosmic adventure? How will the next generation build on what we've learned, and what new mysteries will they uncover? The answers are out there, waiting to be discovered, as we continue to explore the universe with the same sense of wonder and imagination that has driven us for centuries. Science isn't just about numbers, formulas, or cold, hard facts. It's fueled by something far more human: imagination. Think about it. Every groundbreaking discovery, from the theory of relativity to the structure of DNA, began with a spark of curiosity, a bold idea, or a question no one had dared to ask before. And when it comes to dark matter and dark energy, imagination isn't just helpful, it's essential. After all, how do you study something you can't see, touch, or even fully comprehend? The answer lies in creativity, in daring to imagine the unimaginable. Take dark matter, for example. We know it's there because of its gravitational effects, but what is it? Scientists have proposed everything from weakly interacting particles to hidden dimensions, each idea born from a blend of rigorous science and bold imagination. It's like trying to solve a puzzle with missing pieces. You have to use what you know to picture what might be. This imaginative leap isn't just about dreaming up wild ideas. It's about pushing the boundaries of what's possible, challenging our assumptions, and exploring the edges of human understanding. The same goes for dark energy. Its existence was first hinted at through observations of distant supernovae, but understanding it requires more than just data. It demands creativity. Could dark energy be a property of space itself, as Einstein once speculated? Or is it a dynamic force, changing over time in ways we've yet to uncover? These aren't just scientific questions, they're invitations to think differently, to imagine new possibilities and explore uncharted territory. This interplay between logic and imagination is what makes science so powerful. It's not just about collecting evidence or running experiments, it's about daring to ask what if, and being willing to follow that question wherever it leads. And as we've seen throughout history, the most revolutionary discoveries often come from those who aren't afraid to dream big. But imagination isn't just the domain of scientists. It's something we all share, a fundamental part of what makes us human. Whether you're a student, an artist, or simply someone who looks up at the night sky and wonders, the mysteries of dark matter and dark energy invite us all to think bigger, to imagine more, and to embrace the unknown. As we near the end of this journey, let's revisit the central question that brought us here. What's really in control of the universe? Dark matter and dark energy may dominate the cosmos, but it's our curiosity, creativity, and imagination that drive us to uncover their secrets. And in that sense, perhaps the most powerful force in the universe isn't something invisible, it's the human spirit, endlessly exploring, questioning, and dreaming of what lies beyond the horizon. So, what's next? How will we continue to push the boundaries of knowledge, using both science and imagination to explore the unseen? The answers are out there, waiting to be discovered, as we continue this timeless quest to understand the cosmos and ourselves. So, who's really in control, dark matter or dark energy? It's a cosmic tug of war, with each force playing a pivotal role in shaping the universe as we know it. On one side, dark matter acts as the cosmic architect, its gravitational pull holding galaxies together and weaving the intricate web of cosmic structures. Without it, the universe would be a chaotic expanse of scattered stars, unbound and drifting aimlessly. On the other side, dark energy is the cosmic disruptor, relentlessly pushing galaxies apart and accelerating the expansion of space itself. Together, these invisible forces define the universe's past, present, and future, but which one ultimately holds the reins? The answer isn't straightforward. For billions of years, dark matter dominated the cosmic stage, pulling matter together to form the galaxies and clusters we see today. Its gravitational influence shaped the universe's large-scale structure, creating the cosmic web that stretches across the cosmos. But as the universe expanded, dark energy began to take over. Today, it accounts for nearly 70% of the universe's total energy, making it the dominant force on the largest scales. This shift in power has profound implications for the universe's fate. If dark energy continues to accelerate the expansion, galaxies may eventually drift so far apart that they vanish from view, leaving the universe cold and empty, a scenario known as the Big Freeze. But what if dark matter could regain the upper hand? Some theories suggest that dark energy's influence might weaken over time, allowing dark matter's gravity to slow the universe's expansion. In this case, the cosmos could eventually collapse back in on itself, leading to a big crunch. Or if dark energy grows even stronger, it might trigger a big rip, tearing apart galaxies, stars, and even atoms. These scenarios aren't just speculative, they're tied to fundamental questions about the nature of dark matter and dark energy. Are they two separate forces, or could they be connected in ways we haven't yet imagined? This debate isn't just about predicting the universe's fate, it's about understanding the forces that govern it. Dark matter and dark energy challenge our most basic assumptions about physics, forcing us to rethink everything from gravity to the nature of space and time. Each new discovery brings us closer to answers, but also raises new questions, keeping the cosmic puzzle as intriguing as ever. As we reflect on this journey of discovery, one thing becomes clear: the universe is far more complex and wondrous than we often assume. From the invisible threads of dark matter to the accelerating push of dark energy, these forces remind us that there's always more to learn. They invite us to stay curious, to keep exploring, and to embrace the unknown with humility and wonder. And so, as we turn our gaze to the next chapter in this cosmic story, one thing is certain: the search for answers is far from over. Whether it's through groundbreaking experiments, bold new theories, or the collective curiosity of humanity, the quest to understand dark matter and dark energy continues. What will the next discovery reveal? Only time and the cosmos will tell. As we stand on the precipice of cosmic understanding, it's impossible not to feel a sense of awe. The journey to uncover the secrets of dark matter and dark energy isn't just a scientific endeavor, it's a profound adventure, one that reminds us of both how much we've learned and how much remains unknown. Every discovery, from the bending of light around massive galaxy clusters to the faint whispers of the cosmic microwave background, is a step deeper into the mystery of existence itself. And yet, with each step, we're humbled by the vastness of what we don't yet know. There's something exhilarating about this quest. It's not just the thrill of solving puzzles or the satisfaction of filling in gaps in our knowledge. It's the sheer wonder of standing face to face with the unknown. Dark matter and dark energy are more than just scientific concepts. They're invitations to explore, to imagine, and to dream. They challenge us to think beyond the limits of what we can see, pushing the boundaries of human understanding. But with that excitement comes humility. The universe doesn't yield its secrets easily. For every question we answer, a dozen more emerge, each more complex and intriguing than the last. This isn't a failure, it's a reminder of the infinite depth of the cosmos. It's a call to stay curious, to keep asking questions, and to embrace the mystery rather than fear it. After all, the beauty of science lies not just in the answers, but in the journey of discovery itself. As we prepare to wrap up this exploration, let's take a moment to appreciate how far we've come. From the first observations of galaxy rotation curves to the cutting-edge experiments searching for dark matter particles, humanity's quest to understand the universe has been nothing short of extraordinary. And while we may not have all the answers yet, every discovery brings us closer to unraveling the cosmic tapestry. So what's next? The journey doesn't end here. With new telescopes, particle detectors, and bold theories on the horizon, the adventure is only just beginning. The universe is full of surprises, and the next breakthrough could come at any moment. As we continue to explore, let's carry forward the same sense of wonder and curiosity that has driven us this far. Because in the end, the story of dark matter and dark energy isn't just about the cosmos, it's about us and our endless quest to understand the universe we call home. As we near the end of this cosmic journey, let's take a moment to reflect on what we've uncovered. The universe we see, stars, galaxies, and planets, is just the tip of the iceberg. Behind the scenes, two invisible giants, dark matter and dark energy, are pulling the strings, shaping everything from the tiniest galaxies to the vast expanse of the cosmos. Dark matter, with its gravitational pull, acts like cosmic glue, holding galaxies together and weaving the intricate web of the universe. Dark energy, on the other hand, is the cosmic rebel, pushing the universe apart and accelerating its expansion at an ever-increasing rate. Together, they make up 95% of the universe, yet we can't see them, touch them, or even fully understand them. This journey has taken us from the early moments after the Big Bang, when dark matter began to clump together, forming the seeds of galaxies, to the present day, where dark energy dominates, driving the universe's accelerating expansion. We've explored how dark matter's gravity bends light, creating the phenomenon of gravitational lensing, and how dark energy's push is revealed through the behavior of distant supernovae. These discoveries have rewritten our understanding of the cosmos, showing us that what we see is only a fraction of what's truly out there. But the story doesn't end here. The search for dark matter and dark energy is far from over. Scientists around the world are using cutting-edge tools, from underground detectors to space telescopes, to uncover their secrets. Each experiment, each observation, brings us closer to answering questions that have puzzled us for decades. What is dark matter made of? Is it a particle we've yet to detect, or something entirely different? What drives dark energy? Is it a property of space itself, or a sign of new physics waiting to be discovered? The excitement of this ongoing research lies not just in the potential for breakthroughs, but in the sheer wonder of exploration. Every new discovery challenges our assumptions, pushing us to think differently and imagine new possibilities. It's a reminder that science isn't just about finding answers, it's about asking questions, staying curious, and embracing the unknown. As we prepare to wrap up, let's remember that the story of dark matter and dark energy isn't just about the cosmos, it's about us. It's about our place in the universe, our quest for knowledge, and our endless curiosity. These invisible forces remind us that there's always more to learn, always new mysteries to unravel, and always new horizons to explore. So, what's next? The journey continues with new missions, experiments, and ideas on the horizon. The next breakthrough could be just around the corner, waiting to change everything we think we know. As we look to the future, one thing is certain: the universe is full of surprises and the adventure is far from over. And now, as we bring this exploration to a close, let's turn to the final chapter in this cosmic story. What does it all mean? How do these invisible forces shape not just the universe, but our understanding of reality itself? That's where our journey takes us next. As we come to the end of this cosmic journey, it's impossible not to feel a profound sense of wonder. The universe, with all its stars, galaxies, and planets, is just the surface of a much deeper mystery, a mystery shaped by dark matter and dark energy. These invisible forces, though unseen, are the architects of everything we observe, from the smallest galaxies to the vast cosmic web that stretches across the universe. They challenge us to rethink what we know about reality, pushing the boundaries of science and imagination. Dark matter, with its gravitational grip, holds galaxies together, weaving the fabric of the cosmos. Dark energy, on the other hand, drives the universe's accelerating expansion, reshaping its destiny with every passing moment. Together, they remind us that the universe is far stranger and more complex than we often assume. Yet, despite their invisibility, these forces are everywhere, shaping the past, present, and future of everything we know. This journey isn't just about understanding the cosmos, it's about understanding ourselves. Every discovery, from the bending of light around massive galaxy clusters to the faint echoes of the Big Bang, connects us to the universe in ways that are both humbling and inspiring. It's a reminder that we're part of something much larger, a cosmic story that's still being written. But the story doesn't end here. The search for answers continues, driven by curiosity, creativity, and the relentless pursuit of knowledge. With every new observation, every groundbreaking experiment, we're getting closer to unraveling the secrets of dark matter and dark energy. And as we do, we're not just uncovering the mysteries of the universe, we're redefining what it means to explore, to discover, and to dream. So what's next? The adventure is far from over. New missions like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope promise to take us deeper into the cosmos than ever before. Each discovery, each new question brings us closer to understanding the invisible forces that shape our universe. And as we continue this journey, we invite you to join us. Stay curious, keep exploring, and never stop marveling at the wonders of the cosmos. If you've enjoyed this journey through the mysteries of dark matter and dark energy, don't forget to like, share, and subscribe for more cosmic explorations. Together, let's keep uncovering the secrets of the universe, one discovery at a time. The cosmos is full of surprises, and the best part, the story is just beginning. See you in the